Hello everyone, we're going to talk about motor starters today. It's the part one of motor starters. After the exam you'll be doing reversing starters, but today we're going to cover just motor starters in general. We are going to describe the parts of a magnetic motor starter, describe the criteria for determining the suitability of a starter for a specific application, interpret ohmmeter readings that determine the operational condition of a starter. Same thing you did in first year when it came to relays. State the reasons for providing overload devices for a motor. List 3 conditions that would cause single phase of a 3-phase motor. Right? State the requirements of the CEC, Canadian Electrical Code, rules regarding motor overload devices. And lastly, describe the operation and type of overloads, devices used for motor overload protection. Alright, so to get started, we talk about enclosures. Right? There's a real quick statement here. We talked about enclosures in first year from table 65, and I believe it was rule 2400. Right? You got to pick the proper enclosure for the proper device. You got to look at the location it's located in. Is there moisture or corrosive substances or material around, flying particles, dust? Is it a hazardous location? So you have to take all the information you know about the location and the environment that enclosure is going to be in, and you have to take it to table 65 to figure out what type of enclosure you need for your motor starter, or in that case, any enclosure for anything, right? So let's take it to table 65, right? So they can ask you what type of enclosure do I need for a location where there's going to be mist or dripping condensation. Well, you'd have to go and take that information to table 65 and figure out what type of enclosure. Okay, so talking about magnetic motor starters, we talked about a contactor and we talked about overloads briefly. And those things put together create a magnetic motor starter. So the magnetic motor starter, what happens is up here you have your contactor, which again is just a relay on steroids. Okay, it's going to be able to handle higher current loads. It's going to be a coil, and it's going to create a magnet, which is moving an armature, closing contacts. Then you have the overload device, and the overload device purpose is to protect the motor if it's being overloaded for too long of a period of time. It's going to trip out a set of contacts that are in your control circuit that are feeding the coil in the contactor, thus killing the magnet here, armature returning back to the state and turning off your motors. So these two in combination here, contactor and overload device, create a magnetic motor starter. And that's what we use to start and stop our motors. Alright, so talking about selecting a proper starter. Right, so you're going to have to look at, okay, do I want IEC or NEMA? Again, NEMA, what we'll be using in lab here and in North America most likely. NEMA are larger, but they're more versatile. You can use them for a wider range of purposes. Compared to the IEC, they're more made for specific jobs. All right. What you have to look at to select either one of these is the motor FLA. FLA stands for full load amps. So when that motor's running at the top voltage, doing its job, whatever it's moving a conveyor belt of rocks or whatever it's doing, and it's fully loaded, right? What's that current going to be at? So we have to look at that, the horsepower rating of our motors, the voltage, and the service factor. And we'll talk about the service factor a little bit here. Conditions of use. What the actual motor is going to be used for, right? If we starting and stopping often, is it running continuously for days and days on end? What conditions it's in? Is it in a furnace room where it's going to be our boiler room where it's really hot, or is it going to be in a freezer where it's really cold? Got to look at all that stuff. We got to determine if it's reversing a reduced voltage or a full voltage start motor. And that's going to be based on the inrush current. All right. So here's the IEC motor starter use categories, which again we won't really be using, but here's an example of them. Right, so the use categories are AC1 to AC4, and the definitions for each one. So high power factor loads, okay, heating, general distribution loads, and then plugging or inching slip motor rings. Squirrel cage motors, starting under normal running currents, jogging, inching, or squirrel cage motors. So the different applications of the category. And then based on the horsepower ratings, right, I had 460 volts for this guy here. These are my NEMA contactor sizes, right, compared to my IEC contactor sizes. So you can see that the IEC has many more options, right, compared to the NEMA. They're much more versatile. So you can have one that's going to play into, well, they can handle from 15 to 25 horsepower, compared to this guy here, so only 25 or only 20 or only 15, etc. So that's where you can see that NEMA are a little more versatile than the IEC. One's not really any better than the other. They're just for different purposes. But again, we'll be doing the NEMA contactors for this course. All right. Here's the NEMA starting size. Right. So here's your, NEMA starter size. Here's your NEMA sizes, the current ratings, and based on if it's continuous duty or jogging duty, so jogging's on and off, continuous is on for more than 1 hour to 2 hour period. Right, talking about single phase or three phase, and then jogging would most likely be three phase. All right, and it's going to tell you have to pretty much find out what type of motor you need, horsepower rating, etc., current rating, and figure out what NEMA size you would need. All right, which you're not going to have to be sizing the starter for any of our labs or anything, so don't worry about that. All right, here they're asking what can cause motor windings to overheat. All right, so a motor is pretty much just a coil of wire, and that shaft is trying to chase a magnetic field, right? And that's what's causing that motor to run. So you have to look at the load current, right? How much current is actually being drawn from this motor based on whatever it's doing. Again, that current is traveling through your conductors or the windings in that motor, and when I have a current flowing through a conductor, it's going to create heat. The duration of overload, and that's what my overloads are for. Right? If I have a motor that's bogged down and say some really heavy equipment came onto a conveyor belt, it's not supposed to be on there, and that motor is trying to move it, right? It's going to be drawing a lot more current and heating up these windings, which is okay to a certain amount, but we got to look at how long are those windings being overloaded, and at some point those windings are going to burn out. Right? Number of motor starts, right? So starting and stopping motors. When I start the motor, of course we have an inrush of current. That current's going to be quite high, and the higher the current, the more the heat. Okay, so if I'm starting it quite often, that continuous inrush of current can heat up my windings and damage them. The time to reach full speed, right? So if my motor is starting, it might take a while for it to actually get up to full speed, and that means that it's working really hard to get up to full speed, thus drawing more current and creating more heat. The ambient temperature, well, even the motor's not even running. If the room is 50 degrees, that means the windings are at 50 degrees. Once I start putting current through them, it's going to go from 50 degrees and up. So I got to watch out for the ambient temperature and make sure that once I turn my motor on, I'm not going to be overloading that motor or the windings heat-wise. And that goes right back to first year when we were trying to figure out how to size conductors based on ambient temperature and correction factors. And then the duty cycle. Conditions of use, how long is it on, how long is it off, the frequency of use, etc. So those are a bunch of things that can affect the temperature of your windings overheating. Right? And all these factors here are going to be based on the service factor. So service factors are pretty much how overloaded is your motor allowed to be. Right? So a service factor of 1 means that your motor cannot be overloaded at all. Right? It's got to be whatever its current is going to be, it's going to be, and that's it. If you put any more current on it for any length of time, it will most likely damage the windings. Then you get 1.1, 1.15, 1.2, and 1.25. And we'll go through a couple calculations later based on the service factors, but they're pretty much saying here, based on the motor and the windings, how long can it handle overheating based on these conditions here. Right? Obviously, 1.25, it can handle a lot more heat if it's being overloaded. If it's going to be overloaded a lot, it can handle that heat. So these would be like the beasts of the motors that can really handle anything you throw at them, right? Compared to this guy over here, it's got one job, and if that job goes sideways and it's overused or that motor's overheated, it's scrapped. So on motor labels, right, we're going to be calculating overload ratings. Okay, all the information is going to be on your label. Your service factor is pretty much the quality of the motor, like I was saying. It's used to determine a multiplier, which I'll get to in a minute here. And then full load current. This is what the amount of current that a motor is going to be drawing at the normal operation. Whatever its job is to do, when it's starting to do that job or continually doing that job, that's the amount of current on average that it's going to be seeing. Now, obviously, it's going to be there's going to be ups and downs based on different conditions of use. If it's being bogged down by a little bit heavier load or something, but this is the average amount of current it's going to be drawing under normal conditions. All right, so going back to first here, Ohm's law and all the power formulas, it says when a 10 amp 5 horsepower motor is running at 5 horsepower, it will draw 10 amps, right? So it's saying here, when it's running at 5 horsepower, right, it's going to be drawing at 10 amps. If it's drawing or running at 4 horsepower, well, it's not going to be running 10 amps. It's going to be running something smaller. Okay, so we'll get into a little bit of code here to talk about that service factor. Okay, so the CEC 28306, it's rating and trip selection of overload devices. It says number 1, overload devices responsive to motor current shall be set to trip at no more than the following. Right, and it says you are solving for an absolute maximum. So this is really key here. You cannot exceed whatever the calculation comes out to. So here, you can write this down in your code book somewhere, or on your back of your hand somewhere, or whatever you want. But the rule is, if the service factor marked on that motor is 1.15 or greater, right, you're going to take the full load amps of that motor, which is also going to be printed or stamped on that motor label, and you're going to multiply it by 1.25. If the service factor is less than 1.15 or unmarked, then you're going to take the full load amps and multiply by 1.15. So this is pretty much saying I can take the full load amps and multiply it by a certain amount, a percentage, 125% or 115%, to say, okay, this thing can handle up to 125% of its full load amps for a certain amount of time before the overload devices are going to trip. And the same thing here. So, if you're looking at 1.15 or greater, 1.25 multiplied by your FLA, or less than 1.15 or unmarked, it's going to be 1.15. So here's a couple of examples we can go through. Here is your motor, right? That's the label, right? All the spec numbers: horsepower 10, 575 volts, it's 10 amps. All the RPMs, all that hertz, 3-phase. Here, service factor says 1.15. Now, if it's 1.15 or greater, what are we multiplying it by? No one? No one's answering? No? Haha, just joking. Okay, 1.15 is going to be multiplied by 1.25. Or sorry, it's going to be 1.15 is going to be the FLA multiplied by 1.25. Okay, so service factor of 1.15, we can just pretty much change that into 1.25 and multiply it by your 10 amps, right? So the current marked here is going to be your FLA of that motor under normal conditions. So you're going to take your 10 amps, multiply by 1.25, you're going to get 12.5 amps. Now, This is for sizing or setting your overloads, right? And remember back on that slide back here, it said you're solving for an absolute maximum, which means you cannot, for any instance, exceed this value here. So if it's saying I have a calculated load of 12.5 amps, and they're saying, okay, which one do I need to choose? A, B, C, D, or E, right? Well, 10 amps would be too little, right? 12 amps would be just probably perfect. If I choose 15, I've now exceeded that 12.5. So I'm going to pick the 12, right? 10 is too low, 15 is way too high, I'm going to go for the 12, right? I can never exceed this value right here. Here's another one. So 115 volt source. You got to look at what it's looking at, because some of these might be a dual voltage. Yeah, it's 115 or 230 volts, right? Half a horsepower, right? You got your hertz. Its time is continuous use, right? Here we have a service factor of 1, right? Single phase, but a service factor of 1. So you're going to look at, okay, my volt is 115 based on my source. In your amps here, it's saying it's 8.2 amps or 4.1. So it's 8.2 based on 115 volts or 4.1 based on 230 volts. All right. Now we're going to take that 8.2, okay, and we're going to multiply it by our service factor amount. So based on its 1, it's 1.5, or sorry, it's lower than 1.5. We're going to take our our 8.2 and multiply it by 1.15, which is going to give us 9.43 amps. And again, we cannot ever exceed this, so we have to choose from the list here of which one we need. 8 is going to be too small. 9 would probably be perfect. 9.5 is exceeding this number, so I can't choose that. So it would have to be 9 amps. And one more. All right, so here again, 230 volt source. 1.5 horsepower. It's a 115 or 230 volts, so I'm going to choose the 230. The amps is 18 or 9, so it's going to be 9 based on 230 volts. All right, I'm looking for my service factor. Service factor right here is 1, right? So it's going to be 1.15 multiplied by my 9 amps, all right, which is going to give us 10.35 amps here. Again, you cannot exceed that, so looking at 8's too small, 9's too small, 10's probably pretty darn close. Oh, I got 10.25, that's pretty darn close to here. And then 10.5 is exceeding that, so I can't do that. So I'm going to guess 10.25, right? That'd be my best option there. Again, without exceeding. I want to get as close as I can to this number, but I can never exceed it. Okay, hopefully that made a little bit of sense. Okay, overload devices consist of two different sections, right? We have one, it's a sensing device, right? That's going to be actually seeing that full load amp current, right? And that's going to sense pretty much how much current is being drawn through those conductors to that to the motor, right? And the other one is going to be a responding device that's going to be signaled from the sensing device. And this one here is going to be in your control circuit. And if this guy opens up, it's going to kill off the current going to your coil. Thus your armature is going to open up and your contacts will open up, killing the current going to your motor, so stopping your motor. All right, so we have a sensing device and we have a responding device. But they are in two different circuits here. So this would be the higher voltage one, lower voltage, most likely. Okay. So here we have a wiring diagram. Here we have our contactor with our contact, which are normally open, right? We have our seal in or holding contacts. We have our coil, which is in the contactor, right? We have our operating coil. We have our overload contacts, right? So these are the overload contacts, right? That's going to be based on what these overloads right here are sensing. So again, these contactor and the overload device are pinned together and used together. So if my current going through these conductors here gets a little bit too high and the sensing devices, the overload, sense that, what they're going to do is talk to the responding device, and they're actually going to cause these contacts to open up. And when those contacts open up, I then don't have a path for my current to flow through the coil. And if my current's not going through the coil, that means my armature is going to open up, and my contacts are going to open up, killing the current going through my overloads and to my motor. All right, so those are my sensing, right, and the responding. All right, so here's an actual overload. These are the sensing devices, the actual overloads. All right. And these are your overload contacts in here, which can be set to different loads, right? But this is what's actually going to be opening up and killing the power to your coil, thus turning off your motor. It says each ungrounded conductor, that'll be your line 1, line 2, line 3, requires to have a sensing device in them. All right, so here's a little model here. So we have a stop-start station with our holding contacts controlling the coil. All right, the coil is going to move the armature, which are going to close these contacts down here. Then I have a set of overloads that are in series with my motor. All right, and these overloads are connected with the overloads contacts in my control circuit. So if I hit the start button here, there's the sensing and responding. If we hit the start button, current's going to go through the coil, close these contacts, close those contacts, my motor's going to start. Alright, I can then release my finger, this is all from first here, and the holding contacts are going to maintain the current going to the coil, holding my motor on. Then I have my motor being overloaded, something's happening. Right, and the motor's not happy, it's drawing too much current. That current is then going through the overloads. Right? The overloads are then going to trip out the overload contacts in my control circuit, opening them up, and that's going to kill the current going to the coil, allowing my armature to move back to the original position, opening up these contacts down here, and turning off my motor. Alright, normally closed contacts in the control circuit contact will open when the motor conductors are overloaded, higher than rated current. So that's what we just witnessed in that scenario. Again, stop, start, holding contacts, coil, and my overloads for my overload contacts, which are going to be normally closed. Alright, and they're the responding device compared to the overload sensing devices. Alright, it says that the sensing devices are always located in the power circuit. That's true because you want that current that's going to the motor to be traveling through these overloads so it can sense how much current is going to the motor. And that's how it protects it. It's always located in the power circuit and it monitors the current in the motor lines. As you can see here, here's our overloads. Right? Here's the contact, which are normally open. And then we have fuses protecting each line. Right? Now the fuses again are there for probably both overload, but mainly overcurrent. So if I have a dead short and the current gets way too high, way too fast, these are going to protect my conductors and my motor. But the overloads are if my motor is overloaded for a long period of time, they're going to get too hot, open up the contacts, right, in the overload contacts, and then killing the coil. So there's two different ways to sense an overload. So there's one called thermal, which we kind of talked about in the breakers, and magnetic flux, which we also talked about in the breakers. So thermal monitors heat dissipated by the conductors. So whenever you put a current through a conductor, it's going to be heat. And the magnetic flux, it monitors the flux around the conductors. All right? So, two types. There's bimetal strip, the same as kind of like what we talked about in the breakers. And here's a different one, a metal alloy or solder pot type, which we have not talked about. All right? So, how this works is a little weird. All right? So, you have this little tab here you're going to bolt in, right? And these are your conductors, or sorry, this is where your current's going to be traveling through, getting to your motor. All right, so it's going to be carrying the full load current, the FLA. So you're going to bolt that down. What this is, right? There's your bolt holes. And this is a solder pot. So there's solder in here, right, or some type of alloy, and there's a ratcheting wheel here, right? And right now, that ratcheting wheel cannot turn because it's embedded in this alloy or solder, okay? So I'm going to get to the next picture in a second, but before we do that, solder pot or metalling alloy overloads. So they're not adjustable, right? So they're just set. They need time to reset, obviously based on the cooling of the alloy. They're great because they're not affected by vibration. Sometimes vibration can cause nuisance tripping in other devices. Based on this, its vibration effect will not do anything to it. It reacts to single phase condition. So a single phase condition is when you have a three-phase, say, motor, and one of the phases goes out. That means the other two phases are going to be carrying a lot of current. The motor might still be trying to run, but the current is going to be very high on the two other phases, thus having them going through a solder pot, and it's going to help to alleviate the, or pretty much help the motor from overloading. And they're tamper-proof for the most part. You can tamper with anything, but these are mainly tamper-proof. All right, so here's what's going on. We have a normally closed set of contacts here, and there's spring, right? And that spring is pushing up, right? But it can't push up because this little bar here is hitting your wheel, right? Up here we have power from the contactor coming through, and it's going to come through and go to the motor. So this is where your FLA is going to be traveling. All right. We have a heating element up here, which your current's actually going to be traveling through. Right. Your manual reset button here. All right. Here's a stabilizing spring. Right. But then here, right, this is going to be your solder pot. Right, and sorry, down here is your control circuit conductors. Again, this is where your current will be traveling through, going to your coil to allow it to operate or not. Right, so the normally closed contacts, here's your solder pot. Right, so what happens is my current comes down here and it's traveling to my motor. Right, motor's working, but something happens and the motor's working way too hard. That means this heater's starting to heat up just based on the current traveling through it. It's starting to heat up. And at some certain point, this solder pot is going to go from a solid to a liquid, right? And when that happens, this wheel, right, is able to now move. And that spring tension is pushing it up, and this is now going to move, right, because the solder is now liquid, and it's going to open up these contacts here, thus killing your coil, opening the armature in your contactor and cutting off the power going to your motor. All right. So that's how a solder pot 1 works. Obviously, you can't reset it until this is cooled here. Once this is cooled, you can reset the contacts, and it's just pretty much going to push them down when this is solid again, and it's going to come down and probably hit this part here and relatch into lock position until the next time it gets too hot. And it'll allow this wheel to move, and then obviously your contacts would open up again. It's kind of weird. It's kind of cool though. It's very simple. Anyway, that's a solder pot overload. All right, yeah, sorry, they're showing here you can depress it. Once this is hardened, you can push it down and closing those contacts so you can actually start up your circuit again. Obviously, you'd want to try to figure out what caused your motor to overload in the first place. Okay, here's a bimetallic strip overload. It's kind of like the ones we talked about the other day with the breakers. You have adjustable current settings though on these ones, right? Based on ambient temperature compensation. So if it's in a room that's already warm, well, you want to be able to adjust it. The heater size is critical for the accuracy. That's very true. If not coupled, it may not respond to a single phase condition. So you got to watch out. Based on single phase conditions can really be hazardous to your conductors and your motors. So you got to make sure you couple them together, or they're not going to respond to that. Okay. So here's what's happening in the bimetal strip operation. Alright, you have your heating element, right, which is this guy here, and your current's traveling through the motor, right, and then you have your bimetal strip, which is being heated by that heating element, right, and gets hotter and hotter, and that strip is going to start to bend at two different rates, or it's heating up and expanding at two different rates, which causes it to bend actually. Right, so normal current flow, everything's fine. If the heater gets way too hot, right, it's going to cause this guy to bend down and push that push button, that normally closed push button, and open up the contacts going to control circuit, the coil in there, which is going to kill the motor current. Right, and obviously these ones take time to reset. Bimetal strip has got to calm down a little bit and go back, be nice and straight, which is going to then close your contacts and then allow you to start that motor again. So that's this guy right here. Right? Okay, and then we have bimetal strip coupling. Right, and this is what they're talking about here. If they're not coupled together, you might not be able to protect against a single phase condition, which is again one of your phases is gone, but your motor's starting or trying to still run. Right, so here we have phase 1, phase 2, phase 3. Right, we got our bimetal strips for each one. We have a heater, right, which is actually wrapped around each one of those bimetal strips. Right, then we have a coupler bar, right, which is coupling all of those strips together. So if one of them moves, that means they're all going to move. Right, so if either one of these or any of these start to bend, what they're going to do is they're going to push this coupling bar. Right, they're going to hit the ambient temperature compensator, and this guy here, what it does, this is where you can compensate for a higher ambient temperature. You can adjust it so it's not going to trip as easily. Right, but pretty much that coupling bar is going to hit the ambient temperature sensor, and it's going to hit the strike bar. All right, which is going to open up these contacts here, and again, opening up those contacts is going to kill the coil, and it's not going to allow your motor to run anymore until the bimetal strip calms down. These contacts, or the coupling bar, returns back to the original, and your normally closed contacts close again. And there we have again that picture, right? Your overloads, and that's how you can adjust the ambient temperature compensators. Right, so you're not going to get nuisance tripping based on a higher ambient temperature room. Then we have magnetic flux overload devices. These ones are not sensing heat or ambient temperature. They're not sensitive to ambient temperature, which is great, so you don't have to adjust for that. We can adjust them based on moving the arm closer or further away from the coil. It trips right away. And it has a bypass for startup, because when you have a startup for a motor, of course, your inrush current is going to be very high. Thus, your magnetic field is going to be very high. So you don't want it to trip right when you're starting the motor. So it has a bypass for when you're starting it up. And there's two ways to sense the current. The coil is in series with the motor conductor and armature, or there's a current transformer, which we'll talk about in a bit here, around conductors, and it's electronic based. So these ones here are more accurate because it's all electronically done. These ones here are mechanically done. All right. So here is that setup again. Oops. Okay. Based on your sensing device and the responding device, your overloads and the overload contacts. So based on the heated one, all right, you have your coil, which is coming through, hooked up. There's a spring here, and your contacts are closed, right? And your coil can be energized at this point. And then the power contacts are going to close, right? And your current's going to be flowing through to the motor, all right? And if something happens, and so, sorry, they're showing you the responding device and the sensing device here, okay? If something happens, and this motor starts to get overloaded, well, it's going to be drawing a lot of current, and these coils are going to get quite warm, right? Or actually, sorry, not going to get quite warm. The magnetic field around these, around this coil here, is going to increase, based on I have more current being drawn to the overloaded motor. And when that happens, it's going to create a magnetic field here, pretty much creating a strong magnet here, which is going to overcome the strength of this spring holding this contact up, and it's going to pull it down. All right, and it's going to instantly trip it out, cutting the coil, going to my arc contactor, and thus opening up the power contacts, killing the motor. Now you might ask, okay, well, right when the motor gets killed, there's no more current traveling through here, so this is not going to be a magnet, so yeah, those contacts are going to return back to the original state. But it all goes back to 2-wire and 3-wire control. The only way to start up that circuit again is to hit the start button. All right? And before you go and hit the start button, you're going to want to find out, why did my motor overload in the first place? All right, so these ones are really good for instantly tripping it out. Right when that current skyrockets, it's going to move these contacts. It's not going to, like the other ones, it has to heat up enough, and then the bimetal strip has to move, and then it's going to open up. These ones are just instantaneous. So that's nice. Okay, and then we have current transformers. Current transformers, you'll start to learn about, maybe you're learning about them in second year code. Pretty much they're going to be a sensing device that's wrapped around, or that a conductor is fed through. So here's your line 1, line 2, line 3. And they're fed through these little donut-shaped things, which is pretty much just a coil of wire, right? These coils of wire are going to be picking up the magnetic field coming through based on the current traveling through these conductors, and it's going to send a certain amount of current to your current transformer, right? And if pretty much it's electronically done, so if these these coils here start to sense way too much magnetic field based on too much current going through these conductors, it's going to electronically cut out and open up these contacts going to the coil. Again, opening the armature up, contacts open, motor turns off. Okay, so this is electronically done, obviously a little more accurate and instantaneous, but it's based on magnetic field, right? And these coils sensing that magnetic field. So obviously there's going to be a normal amount of magnetic field based on the FLA of the motor draw, right? But if that increases or gets a little bit too high, this is going to be sensing that, and it'll just trip out the coil. All right. So that's an electronic overload relay. Very multifunctional. Uses a current transformer, right, which we just talked about there. Can trip on multiple inputs, so single phase, overload, under voltage. Yeah, so it can sense all of that stuff based on those coils, and much more efficient, obviously because it's electronic. Okay, so talking about schematic symbols for overloads, they can be placed on either side. The IEC standard is to put them before any of your control devices in a control circuit and before your coil. But for the NEMA standard is we usually put them after your coil. So you come to your stop first, and then your start and your holding contacts, then your coil, and then the very last thing would be your overloads for that control circuit. And again, those overloads are what's being triggered by the overloads in your power circuit. And that, my friends, is it. Hopefully you enjoyed that, got a little bit of information from it. Please read through your ILM. If you have any questions, please let me know, and I'll chat with you later. Thanks for watching.